I'm going to go over section 4.2b. So this is Riemann Sums notes. So first off, Riemann Sums is simply using rectangles to estimate the area of a region, and the area of the region that we're going to be focused on is the area under a curve between the curve and the x-axis. Okay. So let's say we're considering this function f of x equals x squared plus 1. So we see the curve here, x squared plus 1. And we're trying to, the area of the region that we're going to be considering is the area that is under the curve, above the x-axis, and between the two endpoints. Negative x equals -2 and x equals 2. So we have this enclosed region that we're trying to find the area for. Okay. However, if we want to find the exact area of this region, we're not going to be able to, there's no easy geometric method to find that area. So right now, let's just focus on finding an estimation for this curve or for this region using rectangles. Okay, so suppose we want to estimate the area of the shaded region using a given number of rectangles, and let's say we've determined that we're going to use 4 rectangles to estimate the area of this region. So we have a couple of ways that we can use rectangles. Okay, the first way is using upper rectangles or circumscribed rectangles. Okay. Notice how these rectangles are drawn. Okay. For these rectangles, you see that you have portions that extend above the curve. So this will be an estimation of sorts, and this estimation is going to be an overestimation. Okay. Using these rectangles will provide an overestimation of the area under the curve. As you can see, the area of these rectangles added together will be more than the actual area of the curve, okay, or of the region under the curve. Okay, we got to be careful of how we draw these rectangles, though. Notice that one corner of each rectangle is on the graph. Okay, so for the first rectangle, we see that we have a left point that's connected to the curve. For the second rectangle, we see that it's going to be a left endpoint. For the third rectangle, you see that's a right endpoint, and the fourth rectangle, you see that it's the right endpoint. Okay. Notice that one corner of each rectangle is on the graph. This ensures that the height of the rectangle is the same as the value of the function at the point where they connect. Okay, so if we're going to be using upper rectangles or circumscribed rectangles, each rectangle that we draw have to have portions that extend above the curve, and we need to make sure that whatever rectangle we draw, each rectangle has either the upper left corner or the upper right corner connected to the graph. Okay, because we're using the graph to find the height of each rectangle. Okay, the second type is lower or inscribed rectangles. Okay, and this is where we were purposely going to be finding an underestimation of the area under the curve using a number of rectangles. So in this case, we're going to stick with 4 rectangles. Okay, but see, here we have portions of the graph that are, the gaps here are going to be below the curve. So we see that if we find the area of these 4 rectangles added together, the area of this region is going to be less than the area of the actual region. So these rectangles provide an underestimation of the area under the curve, and these inscribed rectangles, again, we have to draw rectangles so that each rectangle has gaps that exist below the curve, and we need to choose the appropriate corner to connect to the graph. So for the first and the second rectangle, we have the upper right corner, and for the third and for the fourth rectangle, we have the upper left corner that's connected to the graph. Okay. These next two are the most common ones that you're going to see with problems that deal with AP problems especially. They're dealing mainly with left-handed rectangles and right-handed rectangles. So left-handed rectangles are where we draw a given number of rectangles, and regardless of whether we're not concerned about whether these rectangles are above or below the curve, we just want to make sure that for each rectangle that the upper left corner is connected to the graph. So here for the first rectangle, upper left hand corner; for the second rectangle, upper left; third, upper left; and fourth, upper left. So left corner, upper left corner of each rectangle is attached to the graph. Okay. For right-handed rectangles, we're simply drawing rectangles so that the right corner is, upper right corner of each rectangle is attached to the graph. Okay. Okay, let's see if I can get through an example here. So we're going to use, for example 1, use 4 rectangles to estimate the upper and lower sums for the area bounded by x equals 0, y equals 0, x equals 2, and y equals x squared plus 1. So these 4 lines and curves should give us an enclosed bounded region. Okay. So here we have y equals x squared plus 1. We have x equals 0. We have y equals 0. That's the x-axis. And we have x equals 2. So we have this enclosed region. So the first step, if we want to use 4 rectangles to estimate, we want to use 4 rectangles of equal width. So first we need to split our region into 4 equal widths. And to do that, we have to use the formula for width to determine the width of each rectangle. So the width is going to be b minus a over n. A and b are the left and right endpoints, and n is the number of rectangles that we're using. So for example 1, we're using 4 rectangles. Okay. The second step, we draw the graph, which we did, and we section off each interval. And the third step is we find the sum of the areas of the appropriate rectangles. So we're going to find the area of each of the rectangles and add them together. Okay, those are the steps. So to start off, to find the width is b minus a over n. Our left endpoint is 0. Our right endpoint is 2. So and n is 4. N represents number of rectangles. So b minus a over n. In this case, 2 minus a over 4 is 1/2. So the width is going to be 1/2. Okay, so starting at the left endpoint, our left endpoint is 0. We're going to increment by our width until we get to our right endpoint. So from 0, we keep adding 1/2. So 1/2 plus 1/2 is 1, plus 1/2 is 3/2, plus 1/2 is 2. So here we have our intervals that we're going to be using. Okay. Now, for part A, we're trying to find the upper sum. So we need to draw rectangles so that each rectangle that we draw have portions that extend above the curve. So in this case, the curve is always increasing, and you may just have to practice drawing these. But in this case, it's going to be the right corner, upper right-hand corner of each rectangle that will cause each rectangle to be a circumscribed or an upper rectangle. So for the first rectangle, we see the right endpoint is at 1/2, x equals 1/2. The right endpoint for rectangle 2 is at 1. For the right endpoint for rectangle 3 is at 3/2, and then finally at 2. Okay. So we're basically just going to find the area of each of these rectangles. So the area of a rectangle is simply going to be width times height. Okay. Now the width of each rectangle is going to be 1/2, right? It's going to be the same for each rectangle. But the height is going to be, we're going to use f of x to determine our height. Okay. So let's see if I can spell this out step by step. So if I want to find the area of the first rectangle, it's simply going to be 1/2 times f of 1/2. And f of 1/2 is just going to be the height of my first rectangle, right? If I plug 1/2 into the function, I'm going to get this point, and this point will be the height of my first rectangle. Okay, and we'll figure out what f of 1/2 is a little bit later. Okay, for the second rectangle, it's 1/2 times the height of the second rectangle, which is f of 1. So if I plug 1 into the function, I'm going to get this right endpoint. 1/2 times f of 3/2, and then finally 1/2 times f of 2. Okay. Okay. And then step by step, I can plug 1/2, 1, 3/2, and 2 into the function, and I'm going to get 0.5 squared plus 1, which is 1.25. F of 1 is 2. F of 1.5 is 1.5 squared plus 1. And I'm just simply plugging this into my f of s function, which is x squared plus 1. F of 2 is 5. So I have the heights of each of my rectangles. Okay, so then width times height for each of the rectangles, I'm going to get the area of my 4 rectangles, and I add it together, and I'm going to get 5.75. So the area of these 4 rectangles added together will be 5.75, and we know that this will be a upper sum because this is going to be an overestimation of the actual area in this region, okay? Because we have portions that extend above the curve.